Hello friends, welcome to lecture 8.2 on the topic of orthogonal scaling function basis and multi-resolution approximation. So, we are in the 8th unit which is on discrete wavelet transforms, and this is perhaps one of the key lectures that you should watch out for apart from 8.1 and then the one that is coming next, which is 8.3, because it really establishes the base for discrete wavelet transform, the theory and also the implementation, right. And also it establishes a connection between the wavelet functions, scaling functions, multi-resolution approximations and ultimately the filters that we are going to use in implementing DWT. In this lecture particularly we are going to talk about approximations at a scale. And you must have started noticing this even in 8.1, that the moment we started looking at DWT we have begun to talk about approximations and so on rather than time frequency analysis, and we will understand why that is so. And then we look at the multi-resolution approximation equation, the basic equation that one encounters in multi-resolution approximations. In this and then finally we will move on to the formal study of multi-resolution approximations. In that process we will also take a quick review of what is an approximation, orthogonal projection and so on. So, before we really dwell into the math, let me make a few opening remarks. The first thing that I want to mention, which is not really listed here on the slide, is a point that I just made. When we were looking at CWT, we were talking about time frequency analysis and using complex wavelets and so on, and talking less about approximations. It was more about time frequency analysis. Of course, we did talk about singularity detection, regularity measurements and so on, but not so much about approximations. Now, the moment we have switched over to DWT, we are talking about approximations and so on. The prime reason is, as we move from CWT to DWT, as you must have noticed even in the previous lecture, we start to generate basis functions for spaces, the real number spaces or complex number spaces and so on, whereas that was not the case with continuous wavelet transform. The analyzing functions that we were using in CWT really do not generate basis, but in DWT we have this great opportunity of generating basis functions, in particular orthogonal basis functions, and they are ideal for generating approximations. More interestingly, they are ideal for generating what are known as multi-resolution approximations, and that we shall understand both with an example and with the theory later on in this course. So, the other points that I want to make ahead is the coefficients that we compute. Now, we talk about coefficients just as a way we talked about Fourier coefficients and so on. So, the transform that I compute with a wavelet essentially yields me coefficients, and when I am computing these coefficients at a scale 2 power m or at a level m, what they essentially do is they are capturing the details in the signal at that scale. Okay. And of course, here scale refers to resolution. So, that is a more appropriate term in DWT. Of course, scale will always denote a frequency band, but in DWT it is always a good idea to keep this scale versus resolution relationship in mind as well. So, as I am going up the scale, I am looking at coarser and coarser resolution. So, the analogy of a map, geographical map that we had discussed long ago in one of the introductory lectures really applies here. So, as I am going up the scale or up the level, I am actually looking at a coarser picture of the signal, and what these wavelet coefficients give me are the details that are left out or the details of the signal at that coarse particular scale. And the second point is that the DWT coefficient at any level m are actually spaced 2 power m Ts apart. Now, what does this mean? So, Ts is the sampling interval of the signal. As I am moving up the scale, what is happening? I am actually losing out on the time resolution. that is what this means. So, if I move from scale 0 to scale 2 or level 0 to level 1, then the spacing in time